We're going to look at three types of equations of lines. One of them is a vector equation. We'll also see parametric equations and symmetric equations. First, let's start with the vector equation of a line. In order to understand everything we're going to write down, I'm going to ground us in a visual. Suppose we have a line in space, and I'm going to give you the trace in the xy plane there, that dashed line. And it is parallel to a vector, that blue vector there, who also has a trace in the xy plane. We're going to call the line L, and we're going to call the vector V. And we'll say the vector has components A, B, and C. The vector V points in the same direction as the line. It's not in the same location, but that's not a problem for a vector. But the point in telling you that is that the vector ABC gives a direction for the line L. See, direction in R3 is more complicated than just rise over run, like slope in R2. Now we're going to consider a fixed point on the line L, and we're going to create a vector that goes from the origin to that fixed point. That vector we're going to call R sub 0 and say that it has components x naught, y naught, z naught. And so saying, because the tail of the vector R sub 0 is at the origin, it is a position vector. And so saying that the vector is x naught, y naught, z naught means that the tip of the vector is at the point x naught, y naught, z naught. Now I'm going to draw another vector to a point on the line L, and I'm going to call this new vector just R. The difference between R naught and R, in the way I'm thinking about this, is R naught is a fixed vector and corresponds to a fixed point on L. The pink vector R then corresponds to a random point on L. What we can say though is that R naught and R can be connected by a vector that, because it's parallel to V, can be expressed as a multiple of V, and so TV. Now here's the way this works. Depending on the value of T, I end up with the head of TV kind of tracing a path from the head of R naught, and as T increases, I have tips of vectors that end up lining up along the line L. In other words, L is formed by the tips of the vectors that are traced out as T increases. And I used the word tip, I should have used the word head. So L is formed by the heads of the vectors R as T increases. And using vector addition, we can in fact represent the vector R as the sum of the vector R sub 0 and the vector TV. Remember, R sub 0 corresponds to a fixed point, and V gives a direction. T is what's referred to as a parameter, and different values of T yield different vectors, the heads of which are points on L. Since the line is traced out as T changes, T becomes our input variable. Using the values that we've already written, we can say that R of T then is equal to the vector x naught, y naught, z naught plus T times the vector ABC, where R is a vector function. X naught, y naught, and z naught they correspond to a fixed point on the line L. T is the parameter, and ABC is the direction vector that we called V. And even though x naught, y naught, z naught is a vector, it's actually giving us a point on the line. ABC is giving us a direction. This is the vector equation of a line. Let's see how we can use something like this. We're going to find the equation of the line that goes through the point 6, negative 5, 2, and that is parallel to 1, 3, negative 2/3. And right away I'm going to switch this up on you folks. We have this vector 1, 3, negative 2/3. We can actually use 3, 9, negative 2, which is a scalar multiple of the vector that we were given. Folks, the vector ABC is just a direction. And direction doesn't care how big the vector is. So I just need to be using a vector that's parallel to the one that was given. The reason I did this, obviously, was maybe it's not obvious, to clear the fraction. Anyway, referring to our vector equation of a line, we have that r of t is equal to the vector 6, negative 5, 2, that's where we put the point, plus t times the vector 3, 9, negative 2. Multiplying by t and then adding together our components, well, component by component, gives us 6 plus 3t, negative 5 plus 9t, 2 minus 2t as our vector equation for our line. Now, folks, if we used 1, 3, negative 2/3, we'd have different numbers here. In fact, the numbers would be 1, 3, negative 2/3. It would be a different representation for the same line. That is, we would still end up with all of the same points. They would just occur at different values for t. Now I want to go back to our picture of our line. And here we started with our fixed point, and we talked about TV, and we are increasing kind of toward the right, or closer to the second quadrant, if you will, for the trace in the xy plane. What about values, what about vectors, excuse me, or points on the line that are on the other side of the fixed point? Those are going to occur for values of t that are negative. So if t runs through all real numbers, then we'll end up with both ends of this line. Now back to our answer here, we can actually consider the components of this vector separately. That is, we could say that x is equal to 6 plus 3t, y is equal to negative 5 plus 9t, and z is equal to 2 minus 2t, where x, y, and z are points in space that are on the line. These are called parametric equations. And in general, parametric equations look like x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. We can take these equations, and I'll go with the ones on the left, and solve them independently for t. And if we do so, we'll end up with x minus 6 over 3 is equal to t, y plus 5 over 9 is equal to t, z minus 2 over negative 2 is equal to t. And if these are all equal to t, then they must all be equal to each other. And so x minus 6 over 3 equals y plus 5 over 9, which equals z minus 2 over negative 2. These are called symmetric equations of a line. And in general, they look like x minus x naught over a equals y minus y naught over b, which equals z minus z naught over c. And I put a box around in general this time. I didn't mean that. So we have here three forms for the equation of a line. One of them is a vector equation, and all three forms are going to have x naught, y naught, z naught, and abc. They're also going to have t. But anyway, we have this vector equation, we have parametric equations, and we have symmetric equations, and you'll be asked to work with all three of them.